Imagine waking up to find your own body weight has been cut in half, but your world is falling apart. As skyscrapers snap like toothpicks and the oceans begin to drift upward, humanity faces a terrifying new reality. What happens when gravity fails us for 7 days, and can we survive the crushing return of normal physics? Welcome back to the channel. Today we are diving into one of the most terrifying thought experiments in science, a world where gravity suddenly drops to half its normal strength for exactly 1 week. Not forever, just 7 days, and when it comes back, that might be even worse than when it left. We are going to walk through this scenario hour by hour, day by day, covering what happens to the human body, to our infrastructure, to the oceans, the atmosphere, and the planet itself. By the end of this video, you will never look at the ground beneath your feet the same way again. Before we get into this, if you are new here, hit that subscribe button and ring the bell. We drop deep science scenarios like this every week, and you do not want to miss what is coming next. Let us start with the basics. Right now, Earth's gravitational acceleration is 9.8 meters per second squared. That means every second you fall, you gain about 9.8 meters per second of downward speed. It is what keeps your coffee in your mug, what holds the atmosphere around our planet, and what keeps the moon in orbit. Cut that in half down to about 4.9 meters per second squared, and things start getting very strange, very fast. The very first thing you would notice is that you feel lighter, dramatically lighter. If you weigh 80 kilograms normally, you would suddenly feel like you weigh just 40. You would bounce when you walk. Every step would launch you further than intended. Sitting down would feel like landing on the moon. Standing up from a chair would propel you upward. For most people, this would feel euphoric at first. Joints that ached would feel relieved. Back pain would vanish. Elderly people in nursing homes would suddenly feel decades younger. Athletes would feel superhuman. Children would be leaping across rooms like they were on a trampoline park floor. But your body would also be confused on a cellular level. Your vestibular system, the balance mechanism in your inner ear, is calibrated for 1G at 0.5G. Your inner ear would be sending signals that your brain does not know how to process. Vertigo, nausea, and disorientation would hit millions of people within the first few minutes. It would feel like being on a ship in a storm, except the storm is everywhere on Earth at once. Your cardiovascular system is designed to pump blood against the constant pull of standard gravity. Your heart works at a specific pressure to ensure blood reaches your brain. With gravity suddenly halved, blood pressure regulation would go haywire. Blood would rush toward the head more easily than normal. You would feel flushed, dizzy, and disoriented, similar to what astronauts feel when they first reach orbit, but happening to 8 billion people simultaneously, with no training and no preparation. Hospitals would be overwhelmed within minutes. People with heart conditions, hypertension, or inner ear disorders would be in immediate danger. Surgeries in progress would face catastrophic complications. Medical equipment calibrated to Earth's gravity would give faulty readings. Here is where things get truly terrifying. Every piece of architecture on this planet was designed for a specific gravitational load. Engineers calculate what is called the dead load, the weight of the building itself, and the live load, the weight of the people and objects inside. Both of these loads are entirely dependent on gravity. With gravity at half strength, you might think buildings would actually be safer. After all, they are experiencing less downward force, but that is not the whole picture. The problem is that many structures are engineered to perform at a very specific range of gravitational stress. Foundations that rely on the weight of the structure pressing down into bedrock for stability, known as gravity anchoring, would suddenly be working at half efficiency. Pre-stressed concrete, which gets its strength from tension cables pulled tight against gravitational loads, would experience catastrophic stress redistribution. Some buildings would not fall down, they would spring upward. Tall skyscrapers are particularly vulnerable. These structures are designed to flex slightly in wind, and they rely on their own immense weight to dampen that movement. With half the gravitational load, the dampening effect would be severely reduced, and strong winds could begin oscillating these towers in dangerous resonance patterns. The Burj Khalifa, the Shanghai Tower, the Empire State Building, none of these were designed for a 0.5G environment. Suspension bridges work by having the weight of the road deck pull down on the cables, creating tension that holds the whole structure in balance. Reduce gravity by half and you reduce that tension by half. The carefully engineered balance of forces that holds a bridge like the Golden Gate together would be disrupted. The cables would go slack. The deck would begin to oscillate. In strong wind conditions, this could trigger the same kind of resonance that famously destroyed the Tacoma Narrows Bridge in 1940. Within the first 6 hours, traffic accidents would be widespread, not because roads broke, but because drivers would be misjudging stopping distances and the behavior of their vehicles. A car has mass, and mass still exists in a half-gravity world. But braking friction, tire contact, and vehicle dynamics are all calibrated for 1G at half gravity. Every vehicle on Earth would handle differently, more floaty, more prone to spinning out, harder to stop quickly. Water pressure in pipes and plumbing systems is driven by gravity. Municipal water towers, elevated reservoirs, and gravity-fed irrigation systems would all deliver water at half the expected pressure. For most residential use, this would just mean a weaker shower. But industrial cooling systems, fire suppression sprinklers, and hospital water systems that rely on specific pressure thresholds would begin to malfunction. More critically, dams. Hydroelectric dams and flood control reservoirs hold back billions of liters of water through a combination of structural engineering and, crucially, the weight of the water itself, which presses down on the dam base and creates a sealing force. With gravity reduced by half, the water pressure at the base of dams drops significantly. This changes the flow dynamics through spillways, turbines, and pressure relief valves. Operators would scramble to recalibrate systems that were never designed for this scenario. Earth's oceans contain approximately 1.335 billion cubic kilometers of water, and all of that water is held in its basins by gravity. At 0.5 G, the oceans would not stay put. The most immediate effect would be a dramatic change in tidal behavior. Earth's tides are caused by the gravitational pull of the moon and sun acting on the oceans. But the ocean's tendency to stay in its basin, to resist the tidal pull, is governed by Earth's own gravity. With Earth's gravity halved, the oceans would be twice as responsive to tidal forces. Tides would become monstrous, potentially twice as high or more in many locations. Low-lying coastal cities like Miami, Bangkok, Amsterdam, Mumbai, and Shanghai would face immediate flooding. Storm surges that would normally be manageable could become catastrophic. Entire island nations, the Maldives, Tuvalu, Kiribati, would face complete inundation within the first 24 hours. Ocean waves are driven by wind acting on the surface of the water, and their height is limited by gravity pulling them back down. With half the gravitational pull, waves would grow taller and travel further before breaking. A storm at sea that would normally generate 6-meter waves could produce 12-meter monsters. Coastal defenses designed to handle historical wave heights would be completely overwhelmed. The world's major port cities, Rotterdam, Singapore, Los Angeles, Dubai, would be fighting to protect billions of dollars of infrastructure from a sea that was suddenly twice as aggressive. Container ships in harbor would be battered against docks. Oil tankers at anchor would drag their chains and drift. Submarines operating at depth would find that their buoyancy calculations, all based on standard gravity, were now dangerously wrong. Perhaps even more alarming than what happens to the oceans is what happens to the air above us. Earth's atmosphere is held in place by gravity. The density gradient, thick air at sea level, thin air at altitude, is entirely gravity dependent. At 0.5 G, the atmosphere would begin to expand upward. The pressure at sea level would drop. This would not be immediately dangerous. It would be like moving to a moderately high altitude, approximately equivalent to standing at 2,000 meters above sea level. Most healthy adults could adapt to this reasonably well within a few hours. But people in cities built at already high elevations, Bogota, Addis Ababa, Lhasa, Quito, Mexico City, would find themselves at the equivalent of 4,000 meters or higher. Altitude sickness, pulmonary edema, and hypoxia would hit these populations hard. Tens of millions of people at elevation would need medical attention that global health systems could not provide. Commercial aviation would be thrown into immediate chaos. Aircraft are designed to operate at specific air densities. Jet engines that suck in air to combust fuel depend on atmospheric pressure to function correctly. At half gravity, the air at typical cruising altitude would be significantly thinner than aircraft systems were designed for. Emergency descents and groundings would be ordered worldwide within hours. The global aviation network, carrying over 5 million passengers on any given day, would be frozen. Earth is not a solid, rigid ball. It is a system of tectonic plates floating on a mantle of semi-molten rock, all balanced in a gravitational equilibrium that has taken 4.5 billion years to reach. Disturb gravity, and you disturb that equilibrium. The weight of tectonic plates pressing down on the mantle is what drives the convection currents that move those plates. It is also what maintains the pressure that keeps magma from erupting freely. With gravity halved, the downward pressure on the mantle would be reduced. Magma that was just barely contained beneath the crust could find new pathways upward. Volcanologists would be watching their instruments with growing horror on day 2. Volcanic systems that were dormant or merely active could become explosive. The pressure dynamics inside magma chambers would be completely altered. Yellowstone, Campi Flegrei, Tal, Merapi, Rainier, all of them would be showing anomalous readings. Similarly, the frictional forces that hold tectonic fault lines in place are partly dependent on the gravitational weight pressing the rock faces together. With half the gravitational normal stress on fault planes, previously locked faults could slip more easily. This would likely trigger a series of earthquakes in already seismically active regions. However, the earthquakes themselves would behave differently than normal. Seismic waves travel at speeds related to the density and elastic properties of rock properties that are partly determined by gravitational compression. The wave propagation would be subtly altered, throwing off seismographic prediction models that took centuries to build. The Ring of Fire, the seismically active belt surrounding the Pacific Ocean, would be lighting up on monitoring screens around the world. Indonesia, Japan, Chile, New Zealand, Alaska. All of them sitting on fault lines that were suddenly less mechanically stable than they had been for millions of years. The ice sheets of Greenland and Antarctica are held together not just by cold temperatures, but by their own immense weight compressing the ice below. This compression affects how the ice flows, how it melts from the bottom, and how it interfaces with the ocean. At half gravity, the compressive pressure within the ice sheets would be dramatically reduced. Ice that was structurally stable under 1 g would develop fracture planes under 0.5 g. The massive glaciers that drain Greenland and Antarctica would begin moving faster, potentially much faster, as the gravitational friction holding them in place was halved. Icebergs the size of small countries could calve into the surrounding oceans. The resulting surge of freshwater into the North Atlantic could disrupt the Atlantic meridional overturning circulation, the ocean conveyor belt that keeps Western Europe warm. You are about halfway through. If you are finding this wild, please hit that subscribe button. We have incredible videos coming up on what would happen if Earth stopped spinning and what would happen if the sun suddenly doubled in size. Do not miss them. Every living thing on Earth evolved under the constant influence of 1 g, the body plans of animals, the height of trees, the depth of roots, the wing loading of birds. All of it is calibrated to standard gravity. Birds would be the first animals to show dramatic changes. A bird's flight depends on lift generated by wings moving through air, but at 0.5 g, the bird needs only half the lift to stay airborne. Birds would immediately be able to fly with a fraction of the effort. Penguins and chickens, birds that cannot fly under normal gravity, might find themselves briefly airborne. Albatrosses, which already soar for thousands of kilometers on minimal wing beats, would become almost supernatural in their effortless flight. But not every animal would thrive. Elephants and other large mammals have body structures, particularly their legs and joints, that are engineered for 1 g loading. Their muscle tone, bone density, and joint cartilage thickness evolved to handle their full weight. At half gravity, the muscles designed to support that weight would be underloaded. Over days, muscle atrophy would begin. It would be like placing every large land animal in a form of partial bed rest. In the oceans, the changes would be equally profound, but different in character. Fish use swim bladders to control their buoyancy, inflating or deflating a gas-filled organ to match the density of water at different depths. These swim bladders are calibrated for the relationship between water pressure and gravity. At 0.5 g, the entire pressure gradient of the ocean would shift. Fish would find their swim bladders putting them at the wrong depths. Many species would struggle to maintain their normal depth range, either floating uncontrollably toward the surface or sinking lower than they wanted. Coral reefs, which grow upward toward light at rates governed partly by the gravitational settlement of calcium carbonate skeletons, would experience structural disruption. The complex architecture of a reef, built over thousands of years, could partially collapse as reduced gravity changed the mechanical loading that the coral structures had evolved to handle. Plants use gravity to orient themselves. Roots grow down, stems grow up, through a process called gravitropism. In reduced gravity, this orientation signal becomes weaker. Roots would begin to grow in less directed ways, losing some of their downward thrust. Stems would be less rigidly upright. Crops in the field would begin to lean and sway more easily in wind. Perhaps more critically for human survival, the agricultural supply chain would be in chaos by day 3. Grain storage facilities rely on gravity-fed augers and conveyor systems. Irrigation systems calibrated for specific flow rates would be delivering water at different volumes and pressures. Livestock operations, already dealing with animals behaving erratically, would be struggling to maintain normal feeding and waste management operations. Global food security, which was already stressed before this scenario began, would start to fracture. Not because crops were destroyed immediately, but because the entire logistics and processing system of industrial agriculture is built on gravity assumptions that no longer hold. By day 5, the energy grid would be in serious trouble. Coal and natural gas power plants rely on gravity-fed fuel systems, cooling towers that operate on thermosiphon principles, and water systems for steam generation, all of which depend on specific gravitational constants. Hydroelectric power, which accounts for about 17% of global electricity generation, would be producing at significantly altered output levels as water behaved differently in penstocks and turbines. Nuclear power plants, designed with gravity in mind for cooling water circulation and emergency shutdown systems, would be running in continuous alarm states as operators struggled to maintain safe operations under conditions their safety manuals never anticipated. The global electrical grid, already one of the most complex and fragile systems humanity has ever built, would be experiencing cascading failures. Every blackout would knock out water pumping stations, sewage treatment plants, hospitals, communication networks, and heating and cooling systems. By day 5, the psychological toll would be becoming as dangerous as the physical one. Humans are creatures of routine and stability. When the physical world itself becomes unpredictable, when you cannot trust the ground, when weather is wrong, when infrastructure is failing around you, the psychological response is panic, and panic at a civilizational scale is extraordinarily dangerous. Looting would be widespread in major cities, not necessarily out of malice, but out of genuine survival instinct. People who could not access clean water because gravity-fed systems had failed, or who had lost power and therefore heating or cooling, would be doing what humans have always done in crisis, taking what they needed. Governments would be declaring states of emergency worldwide. Military forces would be deployed in most major nations, though even military logistics would be severely impaired. Aircraft were grounded. Naval vessels were managing in altered sea conditions. Ground vehicles were manageable but challenging. Communications satellites, orbiting at altitudes and velocities calculated for 1G, would be drifting slowly out of their intended orbital paths. Here is the remarkable thing about humans: we adapt. By day 5, people would already be figuring out the rules of this new world. They would know not to jump too enthusiastically. They would know to hold onto railings. Clever engineers would be improvising solutions for critical systems. Hospital staff would be improvising gravity-compensated drip systems. Farmers would be propping up their crops with improvised supports. The same ingenuity and determination that allowed humans to survive ice ages, plagues, and world wars would be on full display. Communities would be pulling together. Neighbors would be checking on each other. Local knowledge, how the specific river or building or road behaved in this new reality, would become more valuable than any global institution. But the clock would be ticking, because everyone would know that in a day or two, gravity was coming back, and that might be the most terrifying thing of all. What do you think you personally would do on day 5 of half gravity? Survive at home, or try to get to higher ground? Tell us in the comments. In our scenario, gravity returns to full strength at exactly the end of day 7, and this moment right here, is potentially the most catastrophic single instant in human history. Everything that has been displaced, distorted, or relocated during the week of half gravity would now be suddenly, instantaneously, subjected to full gravitational force. The consequences would be almost impossible to fully predict, but let us try. Buildings that had been slowly deforming under altered gravitational loads, developing new stress cracks, shifting on their foundations, experiencing unexpected resonance patterns, would now be hit with a doubling of their gravitational load compared to what they had been experiencing. Every structural weakness that developed during the week would be suddenly exploited by the returning gravity. In the worst cases, buildings that had survived the week of half gravity through sheer structural redundancy would collapse in the moment gravity returned. The damage would not be evenly distributed. Modern, well-engineered buildings with large safety margins might survive. Older, poorly maintained structures, which make up the majority of buildings in much of the developing world, would be at severe risk. The death toll from this single moment could be staggering. Building collapses in densely populated areas, combined with people who had been moving and working in ways calibrated for 0.5G suddenly finding themselves at 1G, would create a catastrophic few minutes. The human body would also feel the return of gravity as a shock. After 7 days of 0.5G, people would have made physiological adaptations. Blood pressure regulation would have partly adjusted. Muscle tone would have reduced, not dramatically in just a week, but noticeably, similar to a short hospital stay. The vestibular system would have partially recalibrated to the lighter world. Suddenly returning to 1G would feel, to many people, like putting on a lead suit. Simple movements would feel enormously effortful. Standing up would be a struggle. The cardiovascular system, which had been managing with reduced gravitational demand, would be suddenly overwhelmed with having to pump blood harder against a doubling of effective weight. Heart attacks in vulnerable populations would spike dramatically in the hours following restoration. Astronauts returning from extended space missions often need days or weeks to readapt to Earth's gravity after even longer periods in microgravity. Our population, having experienced only a week of 0.5G rather than zero gravity, would have a somewhat easier adaptation, but the sudden shock of restoration, rather than a gradual re-entry, would make it far more medically dangerous. The oceans, which had risen and sloshed in their basins under half gravity, would now be slammed back by the sudden restoration of full gravitational pull. The water that had risen along coastlines, pushed there by amplified tides and weakened gravitational restraint, would not flow gently back. It would crash. The restoration event could trigger something resembling a global tsunami. Coastal areas that had been managing the altered sea levels during the week could face a devastating surge, as the oceans redistributed under the sudden return to 1G areas that had been flooded during the week would face an even more violent second flooding, as the water surged back with full gravitational force. The expanded atmosphere would slam back toward the surface. At sea level, atmospheric pressure would rapidly increase back toward normal. For most people, this would feel like the popping of ears at the end of a descent. Uncomfortable, perhaps briefly painful, but not immediately dangerous. However, anyone who had been in a pressurized environment, a submarine, an aircraft that somehow continued operating, a sealed industrial facility, could face pressure differential injuries similar to decompression sickness if their environment's pressure did not equalize fast enough with the rapidly changing external atmosphere. Let us imagine we have survived the restoration event. Day 8 dawns, full gravity is back, the world is still there, but what does it look like? The death toll from a week of half gravity would be measured in the tens of millions, conservatively. The majority would not come from dramatic Hollywood-style disasters, though those would certainly happen. The majority would come from the cascading failures of essential services, power outages leading to hospital failures, water contamination from compromised treatment systems, food shortages as distribution networks collapsed, exposure from failed heating systems in cold climates. Medical emergencies triggered by cardiovascular stress and altitude sickness. The restoration event itself could kill millions more in a single day, from building collapses, coastal surges, and cardiovascular events triggered by the sudden return to full gravity. Every major piece of infrastructure on the planet would need immediate inspection and recertification before being put back into normal service. Bridges, dams, nuclear power plants, hospitals, every one of them would have experienced stress events that their original engineering had never accounted for. This inspection and recertification process would take months, if not years. During that time, humanity would be operating with severely degraded infrastructure. Power supplies would be unreliable. Transportation networks would be limited. Global trade, which depends on ports, airports, rail networks, and road systems, would be functioning at a fraction of normal capacity. The economic damage would dwarf anything in recorded human history. The 2008 financial crisis caused global GDP to contract by about 2%. The COVID-19 pandemic caused a roughly 3 to 4% global contraction in 2020. A week of half gravity and its aftermath would likely cause contractions measured in double digits, and the recovery would take not years but decades. Insurance companies would face claims that would bankrupt the entire global insurance industry overnight. The legal frameworks for handling an event with no historical precedent, no clearly assignable responsibility, and damage to literally every sector of every economy simultaneously would be hopelessly inadequate. But humans have rebuilt before, after world wars, after the Black Death, after Pompeii. The remarkable resilience of human civilization, its capacity to adapt, innovate, and reconstruct, would be put to its greatest test. And knowing what we know about humanity, most of us would bet that we would pass it. Now you might be wondering, could something like this ever actually occur? Is there any real mechanism by which Earth's gravity could change? The honest scientific answer is almost certainly not in this way. Earth's gravitational pull is a function of its mass. The mass of the planet, approximately 5.97 times 10 to the power of 24 kilograms, is not going to change in a week. The gravitational constant, which governs how mass creates gravitational attraction, is one of the most precisely measured and apparently fixed constants in physics. There is no known mechanism by which it could be locally altered for one planet for 1 week. However, there are some real-world phenomena that affect how we experience gravitational force. Earth is not perfectly spherical. It is slightly flattened at the poles and bulges at the equator, meaning you actually weigh very slightly less at the equator than at the poles. Earth's rotation creates centrifugal effects that slightly counteract gravity. The gravitational pull you feel standing on the surface is not just from Earth's mass, but is also affected by your distance from the center of the planet. Theoretically, if Earth were struck by another massive object and lost significant mass, or if some exotic physics scenario involving dark matter or modification of gravitational constants occurred, you could see changes in effective gravity. Some theoretical physicists have explored models where fundamental constants are not as constant as we believe. These remain highly speculative, but the question of whether gravity has always been exactly as strong as it is now, and will always remain so, is actually a live area of research in physics. There's also the very real scenario of solar gravitational variations affecting Earth's effective gravity. The Sun's gravitational influence, which we are constantly orbiting through, creates tidal forces on Earth that vary as we orbit. These are tiny compared to Earth's own gravity, but they exist. And then there is gravitational wave research. The Nobel Prize-winning detection of gravitational waves in 2015 confirmed that spacetime itself can ripple. A sufficiently powerful gravitational wave, from say, 2 merging black holes passing extremely close to our solar system, could cause measurable temporary distortions in local gravity. Not 50%, not even fractions of a percent, but the physics of spacetime distortion is real and proven. Even though this specific scenario is effectively impossible with our current understanding of physics, it teaches us something deeply important about the world we live in and our relationship to it. The first lesson is interconnection. Every system on this planet, atmospheric, oceanic, geological, biological, economic, social, is connected to every other system through dozens of invisible threads. Gravity is one of those threads, and if you pull it, the whole web shudders. This is true for other threads too. Climate, ocean currents, food systems, energy networks. We exist in a web of dependencies so complex that most of us will never fully understand it. The second lesson is fragility. Modern civilization is extraordinarily powerful. We have put people on the moon, sequenced the human genome, built global communications networks, and reduced extreme poverty dramatically over the past century. But it is also extraordinarily fragile. It rests on assumptions about physical constants, stable climate, reliable energy, and functioning supply chains that we take completely for granted. Events like the COVID-19 pandemic gave us a glimpse of how quickly global systems can be disrupted by a single variable changing. Half gravity for a week would be incomparably more disruptive, but the lesson is the same. Our systems need to be more resilient, more redundant, and better prepared for scenarios we have never faced before. The third lesson is hope, because in our scenario, humans adapt. Within hours, people are learning the new rules. Within days, communities are innovating solutions. The same brain that split the atom and composed symphonies and built the internet would be working furiously to solve the problems of a half-gravity world. We are the most adaptable large animal in the history of this planet, and that adaptability is our greatest asset. Understanding our vulnerabilities, running thought experiments like this one, is actually part of how we build that resilience. Engineers who think about failure modes design better buildings. Emergency planners who consider impossible scenarios develop more robust response systems. Scientists who model the extremes of physical reality discover new understanding about how the universe works. We started this video with a simple, terrifying question. What would happen if gravity weakened by 50% for 1 week? The answer, it turns out, is almost everything. Your body would struggle to adapt. Your city's infrastructure would begin to fail within hours. The oceans would rise and rage. The atmosphere would expand and thin. The ground itself would become less stable. The entire food, energy, and water systems that keep 8 billion people alive would be under simultaneous assault. And when gravity came back, the reckoning would be swift, violent, and devastating. But even in the middle of all of that catastrophe, humans would be doing what we have always done, helping each other, figuring things out, building something new from the wreckage of the old. That is, when you think about it, the most remarkable story of all. The next time you feel the solid ground beneath your feet, the next time you sit in a chair or drink a glass of water or watch rain fall down from the sky, remember that all of it, every single bit of the world you take for granted, exists because of that invisible force holding everything together. Gravity is not just a fact of physics. It is the foundation of every single thing that makes your life possible. If this video made you see the world differently, do us a favor, hit the like button. It genuinely helps more people find this content. Subscribe if you are not already part of this community, because we have videos coming up that are going to blow your mind just as much as this one did. And drop a comment below. We want to know which part of this scenario scared you the most. The first 60 seconds of chaos, the restoration event, or something else entirely. Let us talk about it. We will see you in the next one. Stay curious, stay grounded literally.